Old naval ship fired 10-kilogram cannonballs from a 200-kilogram cannon. It was very important to stop the recoil of the cannon, since otherwise the heavy cannon would go careering across the deck of the ship. If in one design, a large spring with a constant of 20,000 newtons per meter was placed behind the cannon. The other end of the spring was braced against a post that was firmly anchored to the ship's frame. What was the speed of the cannon's ball if the spring compressed 50 centimeters when the cannon was fired? And so my first step was to think, okay, well, the first part of this question is momentum thing.
Okay.
And so I did M1V1 is equal to a negative M2 V final plus an M1 V final. But I don't know if that's right. That's where my train of thought went.
So it's got your cannon, and then it's like attached to the ship like that, right?
Yeah.
Does anyone smell coffee?
Or is it the other side?
It smells like a roasted.
I had Taco Bell.
Yeah.
Okay. How do we do momentum? Because otherwise it's... Sure, we can try momentum. No, we can't do momentum.
How come? Compares to masses.
True. It does.
Would this be explosion and momentum?
Yeah, like you'll be using energy and momentum.
So which one would we do first?
Let's see. So before... One half mass times v squared plus 1/2 kx squared is equal to 1/2 mv squared plus 1/2 kx squared. What's before? Is there anything happening before?
No.
People are about to board the ship?
Shoot a cannon.
Okay, so we know that it compresses 50 centimeters. So we can start here.
And because we also know the K
We can
constant.
find the total amount of things. Does it say how fast? What are we looking for?
We're looking at how fast the cannonballs are projected.
The cannonballs are projected.
Yeah, if it's pushing back the cannon to where the spring compresses that to that size, what speed the ball going? Stuff was gunpowder. Spring.
Cannonball, the ball, and the cannon. So beforehand, zero momentum, right? They're both not moving.
Right, yeah, that's true.
Okay, so that's just going to be 0 on this side. Mass of the ball, it's 10 kilograms.
Mm-hmm.
Velocity is unknown, and then mass of the cannon. 200. Okay. That's right.
It would be a negative 200.
Yeah. So this is what we're starting with right here. Then we go from here, then we go to our kinematic equation. Or not a kinematic, our energy. So like the energy of the cannon, for example. We say at the beginning, right after the cannon fired, there are two phases. Right after it fires, where there's all velocity, kinetic energy, and then a little bit after a little bit after the cannon fired, where there is spring energy.
Okay.
So you have two steps. One is when you're right after it fired, like right as it's going that way. And then your second step is when this spring is compressed. So this is your before and after. We'll just ignore the cannonball for right now in our energy equation, because it's going to be the same. Like it's in energy right after the explosion is the same throughout. It doesn't change at all. So we're looking at the cannon, because right after it fires, the spring's like that, then it starts to compress. So before, what is there? Before, or in your before equation? Like what do you got?
And before, momentum will equal 0. They both will equal 0.
Yeah.
Energy.
So then, oh my gosh, my brain is broken. So we have 3 steps, 3 phases. Yeah. 1. So phase 1 is where you have your cannon and cannonball inside there. That's your momentum before. Then phase 2 is cannon explodes. Spring is still uncompressed.
Okay, so this is just as.
And so it's just as it's exploding. Then phase 3, spring's compressed,
And it's all the way back.
and the cannonball's out this way.
Okay.
What we will use is momentum equation for this one. That's this thing right here, because right here there's 0 momentum at the beginning, and then it goes forward at this part. So that's what we did with this. Then our energy equation, we're going to use the cannon for this one. For these two, with these two. So this becomes our new initial.
Mm-hmm.
So at the beginning, the cannon has some velocity that he gained from the explosion. We find that from that thing. That's the cannonball's final velocity. And that becomes the cannonball's initial velocity, right here. Because it went from here, this is the initial, then this is final. Then we basically go and
Take that
and make this velocity the initial velocity of the cannon. And then this is the final velocity, which is 0.
Makes sense.
So here we use our energy equation before there's only kinetic energy. And after there's only potential energy, your spring energy
Of which one?
of the cannon.
Okay.
So that's 1/2 m times v, v2 final squared. We'll just keep the same variable name. That's equal to 1/2 kx squared.
Are we doing kinetic final and spring final? Or does it even matter?
The kinetic final, since it's the maximum compression is that much, that means that it stopped moving when it reached that compression thing. So then there won't be any kinetic energy at the
I
end.
meant for phase 2.
Phase 2?
Yeah.
Um,
That'll be full kinetic.
yeah, that's full kinetic.
So that'll just be our.
Yeah. Does that make sense? 'Cause this is your problem. It's kind of a big deal.
No, it makes,
I'm just kidding.
it makes perfect sense.
Okay, good. Now what can we do?
And now we solve for velocity final and plug it in.
Okay, so V final, V2 final is equal to kx squared all over m square root all that. Awesome. Plug that back into here and solve for V cannonball.
Oh wow, so you solved this one for V2 final.
Yeah. A picture helps. I kind of like this because then you can see where all the things are going to go, like all the variables. 'Cause it's kind of confusing how your V final becomes your V initial after a while.
So you'd have 200 times
All that.
the square root of k x squared divided by m is equal to 10 times velocity initial. Or 10 is equal to 10 times
V naught, V cannonball.
square root. So in that case, well here, where would you plug it in again?
So you take this V2 final and plug it in right here.
Okay.
And then you solve for V1 final. So that's going to be 10 times V1 final
Oh, I see what you did there.
is equal to 200 times the square root of kx squared all over m. Divide that by, there you go. That's your V final cannonball, final power cannons.
Cannons?
Cannons, cannons.